Hey guys, Mrs. Thompson here, and this is going to be the beginning of our new unit. We're going to spend some time looking at solids, liquids, and gases, the phases of matter, or the three main phases of matter, and then we're going to go more in depth with gases. Okay, so today it starts out with conversions from units of pressure, volume, and temperature. Pretty easy beginning, so here we go. First thing. We need to know how to convert from units of pressure because we're going to deal with gases. And gases, the way we kind of measure them are by, actually, volume, pressure, and temperature. So first one, pressure. Squish. All right, here's the definition of pressure. It's defined as a force per unit area. Okay. So I have this little lady here just to illustrate that. You can tell on the left side of the picture, this one, all of the weight that she has is being pushed down on this amount of area. So her weight's distributed in this whole area. Then, when she does a nice little ballerina move, all of her weight is distributed on this small little point. So it creates more pressure, and you see the ground pushed in, because all of her force, pushing downwards, is covered in a small little area. Alright, so here we go. More specifically, we need to know about gas pressure. So how is gas pressure created? Well, it's created when the particles of a gas collide with container walls. So this just means all those gas particles are moving around, and when they hit the walls of a container, they create a little force, and that force we call pressure. And so there's a picture of gas molecules, they're moving around, and the pressure is created once they hit the container. Not when they're hitting each other, but when they're hitting the sides of the container. All right, so we need to know how we measure pressure. We use a barometer to do this. Okay. Couple of different barometers. Here's a spring barometer, and what you see at the bottom is a spring. Pressure is pushing on the spring, and when pressure pushes on the spring, the little dial turns more to the right so that it looks like it's got higher pressure. When there's less pressure, the spring goes up, and so the dial moves to the left, showing that there's less pressure. Or here is a traditional barometer using mercury. Mercury is one of those substances or metals that are in the liquid form. And so what we have in a mercury barometer is you have a glass tube that's in a vacuum. You have liquid mercury at the bottom, and it's exposed to the atmospheric pressure. Now when the atmospheric pressure pushes down, the mercury gets pushed up into the barometer, and then we just kind of measure this distance to see how far it's gone up and how much pressure is. We do this in millimeters of mercury because we measure it as a distance. All right, you need to know what are normal conditions for pressure because we're going to use those a lot. Normal just means like, well, it's normal, which is like what we have. It's actually at sea level. So at sea level, the pressure is 1 atmosphere. And the reason we call it 1 atmosphere is because there's 1 atmosphere of pressure above us. There's 1 atmosphere of air above us. We can also change that 1 atmosphere into a bunch of different units. And so you see 1 atmosphere is equal to 760 torr, 760 millimeters of mercury. That's Hg. Remember, you can read the barometer of a mercury barometer by measuring the height. That's why you see millimeters of mercury. 101.3 kilopascals and 14.7 psi. That's pounds per square inch. That's what we use to measure like our tire pressure because we're in the United States. We got to use pounds. All right, so here we go. Since these are all equal, we can make a conversion factor of any of these two. So if we do that, all we would do is put the unknown unit at the top and the given unit on the bottom, and we would put whatever number they come with. So I could make a conversion factor of torr and psi by just writing torr, 760 torr, either on the top or the bottom, whichever way I need to cancel units, and then PSI, 14.7 PSI on the other side. All right, let's try this first one. It says convert 761.3 millimeters of mercury to kilopascals. All right, so we'll start with 761.3 millimeters of mercury are given. We're going to multiply by the conversion factor. Conversion factor is the given unit on the bottom. So the unit that we're looking for to cancel anyways is millimeters of mercury. That's why we drag it to the bottom. On the top, we're going to put the desired units, the units that we want to find, and that is kilopascals. Okay, so now I've got my units there. I need to find the numbers. Well, I have the conversion factor at the top. In front of millimeters of mercury, I have 760. And in front of kilopascals, I have 101.3. Okay. Now that I've done this, my units cancel. And I'm going to end up with the units that I need. So here we go. We'll multiply across the top, divide by the bottom, and I get 101.5 kilopascals. Now, in terms of significant figures, what I'd like you to do is round to the number of significant figures based on the given. So I want you to go ahead and assume that all of these are a definition and have unlimited significant figures. Not 100% true as they are measured, but for our sake, we're just going to round to the same number as the given. So if I do that, 4 sig figs is my answer, so I'm going to box that as my final answer. Okay, hopefully easy. Next, we'll do another one, just in case that wasn't easy. We're going to convert 1.07 atmospheres to millimeters of mercury. So I'll start with the given, multiply by the conversion factor. Remember that is the given unit on the bottom. So this time let's just go ahead and look for the number with that. So in front of atmospheres, that's the unit I want to cancel, is a 1. So 1 atmosphere. And we want to find millimeters of mercury. In front of that is 760. So we'll put that on the top. We will cancel out the atmospheres. Great. And that equals 813 millimeters of mercury. That is the same number of significant figures as the given. We'll box that. All right, piece of cake. Next, we're going to talk about temperature. And so first we need to know what temperature is. It's not how hot or cold something is. It's actually a measure of the kinetic energy of the particles. So what's kinetic? Kinetic is just movement, it's motion. And so when we're measuring temperature, we're measuring how fast those particles are moving. And so here we go. We've got a picture here. It says air molecules collide with the thermometer. Their energy is transferred to the mercury inside. So inside the thermometer, the mercury is able to rise. And it does so when the molecules are moving fast enough. Well, when they're moving really slow, like the picture on the left, they don't rise. And when they're moving rapidly, they cause the mercury to move rapidly. So they move up the tube and you see a higher temperature. Okay, so there are 3 different scales that we use to measure temperature. First being Fahrenheit, which is what we get our weather in, like it's 48 degrees outside, so it's 48 degrees Fahrenheit. Then you have Celsius or centigrade, which is what most of the rest of the world uses. And finally you have Kelvin. And Kelvin may be something new, but it was new to you. It was created by a scientist named William Thomson, another Thomson out there. He was also called Lord Kelvin. But he created this scale that starts at 0. It doesn't have any negative temperatures. And it starts at 0 because that's when there would be 0 movement of particles, that is. And it goes way up. Here's a cute little meme. I'll let you digest that. 3 favorite scientists. There we go. Okay, so 0 Kelvin actually has a name. It's called absolute 0, and it's a theoretical measurement where we state that we think that all movement is going to stop at that temperature, and we find that by kind of like extrapolating data to see where that would happen. Okay. In terms of absolute 0, it is something that is very difficult to obtain because when you measure something, measure its temperature, you have to have a device to do that. And so when you add that device into the mix, you're actually adding energy. And so by adding energy, you can't actually get there. So you can get close, and we've actually gotten to, scientists have gotten to 1 billionth of a degree Kelvin. Here is Bill Nye to talk about it.
Molecules completely stopped. Absolutely stopped. Well, that would be what scientists call absolute zero. It would be colder than almost anything you can imagine. And the reason is there'd be no molecular motion whatsoever.
If you've never seen Phases of Matter, Bill Nye, you might want to watch that. It's a cute one. All right, so we have to actually convert between the units of temperature. I won't ask you to convert between Fahrenheit and Celsius. There's no point. We're going to measure in Kelvin, or excuse me, Celsius. So we can change that into Kelvin using this equation. Kelvin is equal to Celsius plus 273.15. You might see it written sometimes as just 273. All right, so let's do an example. Convert 25.0 degrees Celsius into Kelvin. So Kelvin is equal to 25.0, that's the Celsius temperature that I was given, plus 273.15. Yes, an easy equation. I hope you can see that. When we add those two together, it's 298.15. Okay, well, what about significant figures? When you're rounding to the correct number of significant figures, this is addition. So you're rounding to places. So in 25.0, I have one place past the decimal. In 273.15, I have two places past the decimal. So since I only need one place past the decimal, that's the least, I'm going to round this to 298.2 Kelvin. Notice there is not a degree symbol next to that. Please don't make the mistake of putting degrees Kelvin. Unfortunately, it's degrees Celsius, it's degrees Fahrenheit, but it's not degrees Kelvin. So there's my final answer. No degree symbol. All right, we'll do an example going the other way, going from Kelvin to Celsius. Pretty easy. Here we go. We've got 100 Kelvin is equal to Celsius plus 273.15. I need to rearrange the equation, so to solve for my Celsius. So Celsius is being added to 273.15, so I'm going to need to subtract 273.15 from both sides of the equation. And so that's going to be Celsius is equal to negative 173.15. All right, what about sig figs, Ms. Thompson? Well, oh, actually, that side cancels. You're going to cut that to places again. And so one place past the decimal, the 5 will bump up the 1 to a 2. So my final answer is negative 173.2. And voila, another easy peasy equation for you. All right, last one, volume. So just a refresher, volume is the amount of space that an object takes up. So here's a cube, its length times width times height. If we needed to do that. All right, we're going to use several conversions. That is the fact that 1 liter equals 1,000 milliliters. Or you could say that 1 milliliter is 10 to the negative 3 milliliters. This is easier, so we'll use that one. 1 cubic centimeter is actually equal to a milliliter. So if you take one of these little cubes that are 1 by 1 by 1 centimeter, that would be a milliliter. And then something nice about water, which you'll see a lot, we'll need to use this. The density for liquid water is about 1 gram per milliliter. Now this changes with temperature, and it varies just a little bit as the temperature increases and decreases away from like normal temperature. So we can use this most of the time, but not all the time. Sometimes you'll actually have to look up the density of water at that particular temperature. All right, so let's just do a quick conversion of volume. Convert 250 milliliters to liters. This is mostly what you'll be doing, converting milliliters to liters or vice versa. So 250 milliliters times our conversion factor. I'm going to need the one that changes liters to milliliters. So I know that 1 liter is 1,000 milliliters. Milliliters needs to be on bottom to cancel, so we'll put that on bottom. Liter on top. Milliliters cancel, and we get 0.25 liters. Notice I dropped the 0. The reason I dropped the 0 behind the 5 is because on the left side, there's only two significant figures, or the given has two significant figures. If I add the 0 over here, right there, if I add that as a 0, that would give me 1, 2, 3 sig figs, and that's not correct. So here's our final answer. All right, hope you found that easy, and I'll see you in class.